Hello. I want to see if, the stream can actually hear everything, my voice and everything, if it's fine or not. Okay. Hello. Everything, my voice and everything, if it's fine or not. Oh, okay. Maybe. I'm gonna attach a headphone so there's no echo. Just give me a moment. I'm gonna attach a headphone so there's no echo. Just give me a moment. I'm gonna attach a headphone so there's no echo. Hello, hello. 1, 2, 3, mic testing. Hello, hello. 1, 2, 3, mic testing. Yeah, I think it's good. I think it's good. Let me just mute that again. And let's get started. So, as the description states, today we're going to be doing, well, chapter 20. Oh, no, this is the wrong one. Sorry. Where is it? This. Today we're going to be doing chapter 28 and possibly chapter 29 of physics textbook. This is again a university level course of electromagnetism. So let's get started. The topic is chapter number 28, magnetic fields. Now, what is a magnetic field? A magnetic field produces a magnetic force on a moving charged particle or a magnetic object. Let me just quickly write that down. Magnetic field produces a magnetic, apologies for my handwriting, a magnetic force on a moving charged particle or a magnetic object. So basically what this is saying is when we know that when a moving charged particle, let me change this to white. We know that when a charged particle actually moves, for instance, this is a particle and it is moving a charged particle with, let's say, charge q, and it is moving with velocity, let's say velocity v1, then this whole charged particle actually generates, or let's say has, a magnetic field of its own, just like a magnetic object has. So when a charged particle is moving, it is similar to a magnetic object. And a magnetic object in a magnetic force, in a magnetic field, experiences a magnetic force, whether that's a push or a pull. So that's, just the basic starting point of it all. What we stated, a magnetic field is an area which produces a magnetic force on two main objects over here, a magnetic object or a moving charged particle, which in turn acts like a magnetic object. Let's move on. Now, of course, since we've done the definition, we also need to do the formula now. So So to, let's say, sort of understand the formula of the magnetic field, we have to sort of understand the root formulas. For instance, before we have already learned about the formula E is equal to Fe over Q. Oh, here this is obviously the formula of the electric field. For instance, E is equal to the electric field. F is equal to Fe is equal to the force of the electric field, and obviously Q is the charge. So now that we, sort of have this in the back of our minds, we will move on to the magnetic field formula, which is which is B. And B is equal to FB over QV. You can see that these are sort of similar. What am I doing? I apologize. These are sort of similar. For instance, we have E, or here we have the B, and Fe, which corresponds to Fb. The only sort of more notable difference over here is Q, and here we have QW. This is because our definition actually depends upon the velocity of the particle. So it's important that we have the velocity of the particle. And obviously, since this is a vector quantity, so it depends on what angle that all is, but we'll get into that. You don't need to be confused with all that. Just give me a minute. Okay. Just give me a minute. QV. I really should sort of like increase the thickness of it. Or maybe we could wait. Just give me a minute. You don't need to increase the thickness, we could just zoom in. There we go. Now, this is obviously the formula of, well, B. We can also rearrange this formula to get our formula for the magnetic force. which is obviously FB. So FB is equal to BQV. Now you might see that this is awfully familiar. F is equal to BQV. This is because I believe we've already done this in our A levels. So it's a similar formula to that BQV. Only difference is now it's what do you call it? The Q is in these, I forgot what they were called, these modes. Anyways, Q is always positive. And if we want to further, let's say, break this down, we could also write it as FB is equal to Q vector, velocity vector into B. This is our cross product. So our two main, let's say, values is QV and B. These are being, its cross product is giving our answer of FB. Another way to write the magnitude of FB would be by, well, just doing this B sine theta. You might be wondering, what is sine? What is this theta? Well, theta is the angle between the direction of the velocity and the magnetic field. Velocity and the magnetic field. Just for a little visual, let's write, this is theta, and let's call this V1, let's call this B. So that's just to give you a clearer idea. Moving on. Let's also write a definition of what is magnetic force, which, well, through our equation we can write that magnetic force is the cross product. God, my handwriting, I apologize. I really do. Cross product of velocity vector and magnetic field vector. This is the important part. Scaled by charge. Now let's continue on this on magnetic force. When FB is equal to 0, then, well, the charge is either stationary because obviously stationary charges, as we stated before, stationary charges don't act like magnetic objects, so there's no force acting on it by the magnetic field. So either the charge is stationary or the particle let's write this, I guess, in white. Let's see, so differentiate it. The charge is either stationary or the particle is moving parallel to the magnetic field. So if the charge is obviously moving parallel to the magnetic field, so V1 is going in this direction and B is also going in this direction, our theta will obviously be equal to 0 because there's no angle between two lines. So our FB will also be equal to 0. Second part, when our FB will be equal to 1. This will happen when the particle velocity and magnetic fields are perpendicular. So So the magnetic force will be one when particle velocity and magnetic fields are perpendicular. That will be maximum. So when we will have a right angle between our V1 or what just or simply velocity vector and B. This will be theta, 90 degrees. And when we plug 90 degrees into our equation sine theta, then theta is equal to 90, we will get 1 and sine 0, and theta will be equal to 0, and we will obviously get 0. That's that figured out. Oh, then. Next part, let's move on. Magnetic field is sorry, the magnetic field is measured in a unit called Tesla, obviously named after Nikola Tesla. So its SI unit is just a T, and it consists of 1 Newton over Coulomb. I think, no, I'm not writing that correct. Apologies. I can't write. I don't know why. Coulomb and meter per second. So if you want, know the what are they called? Basics of SI units? I don't remember, but you understand. This is sort of like, I don't know, the derivation of Tesla, the breakdown of the Tesla SI unit. Anyways, that's that. Let's move on. We also have an important thing to discuss here, which is our right hand rule. So, a right hand rule, well, as this picture states, that to find the cross product of V and B, we can use, well, this method. We have to, well, take our palm, as we stated in section and in the first image, in the image A, and then we have to lay it flat according to our B, our magnetic lines. And then we have to swivel it towards our speed vector, towards our towards our velocity vector. What is that? I apologize. Just give me a moment. Hello. Okay. So basically, you kind of use any table or any flat plane that you have as the plane for our two products of our cross product. For instance, V and B. It's pretty straightforward, if I'm going to be honest. So you just start with B and you sort of angle where V and B is. From what I can, from what I and you can see in these images, we have to start on B and sort of move our hand from the backside, leading our backside towards our V vector, our velocity vector. And where our thumb will point, well, that will point to our cross product. An important note that it's stated here: if the force on the particle is positive, what the hell? It's white. That's white. If our particle in question is positive, then our thumb will point towards our cross product. If it is negative, then our thumb will point in the opposite direction. That's all you need to know about this. Let's move on. Next up, we have, this is a small, let's say, concept that's sort of talked about in the book, which is circular motion of electrons and protons. Actually, I think it's better if I show you guys the image. So what's happening here is we, in our previous chapters, discovered, in our previous chapters, we learned about pair production and annihilation. This is sort of showing what happens when pair production occurs in a magnetic field. So what happens in pair production is we have a gamma particle which splits up into a positron and an electron. So let's see what this states. Shows tracks left by charged particles moving rapidly through a bubble chamber. The chamber, which is filled with liquid hydrogen, is immersed in a strong uniform magnetic field. As we stated, that the pre-production, or whatever you might call this, is happening in a magnetic field. And since these particles are charged and they are moving, they do experience that, what do you call it, that magnetic field, which leaves no track because an incoming gamma particle which leaves no track because it transforms to electrons, but electron and positron, molecule knocks an electron out of a hydrogen lecture. So one electron kind of just drifts straight off because it's probably not that charged, and it's in hydrogen as it's stated. Long track marked 8, this one is hydrogen. This is our electron and positron, which, as you can see, are spinning in the opposite direction because they have opposite charges. That's basically all that is here. What's the time? Okay, we got time, we got a bit of time. Let's move on. I think we'll go until, I don't know, maybe 10 and see how much we can do about this topic, how much topic we can cover. You know what? I think we will do sample problems, maybe possibly in another episode, in another live stream. I'll do later, or all the relevant sample problems or exercise problems, etc. Right now, only theory. I'll see how this works, and probably moving forward I won't do this, but right now I'm just gonna be like doing this, kind of splitting these up. If you want to see the sample problems, that video will probably be up, you know, by the time you're watching this, or in a few days. So stay tuned. Anyways, let's move on. So now we're going to be talking about crossed God damn it. Crossed fields. And the book has this highlighted as the discovery of the electron. Well, that seems interesting. Let's see what it holds. So, there are two fields going on. There's an electric field and a magnetic field. Now, both of these fields both of these fields produce a force on any incoming charged particles. So now we sort of send. We can't write it like this. Let's change it up. We send particles through these crossed fields and sort of see how they, let's say, how they react. Just observe them. So we send, well, lots of things there, but let's see what the steps are. First of all, we turn both fields off to find the center spot. Okay? Turn both fields off to find the center spot. Then we turn on the electric field. And then we turn on the magnetic field. So the reason we do this is when we turn on the electric field, our charged particles will deflect one way or another. And then after, that deflection is done, we turn on our magnetic field and try to adjust just it so that there is no deflection. So let's do this in one center point, into on the electric field. What did we state as the electric field? Oh, I don't remember. Oh, I don't remember. Well, anyways, let's just say that this happens, and then 3, we start. We try to adjust this slowly, until we have, well, let's just create this up straight line. Until we have, God, this is ugly. Until we have our straight line. When, these two fields are adjusted, then we can state that the magnitude of the two fields are equal. So what we do is Q is equal to Q V B sine 90, because obviously it's perpendicular. This then goes to V is equal to E over B. So since these two are equal, we can actually measure the speed of the particle, let's sort of go into the nitty-gritty details of how we actually got this equation. We start off with our basic sort of like kinematic equations. V1, V initial, C plus number 2A to square. And our A is equal to QE M. How did we get this? Well, it's quite easy. We got this from F is equal to EQ, and F is equal to AM is equal to EQ, and bada bing, bada boom. That's how we got now. We sort of, let's say, have these all together, and through some magic, it's not that detailed in the book, but what it does say is that L is equal to VT, VI is obviously equal to 0, so VT 0, and that is 4. That makes more sense. Okay, L over V for me. But anyway, if we simplify this, what we do get is y is equal to QE square over 2mv square. This is our formula. Another formula that we are also shown is these two are used in this cross fields to find specific variables. I am surprised, like the derivation of these is not that clearly given in my slides at least. So I'm not gonna go through them. I apologize. But if you want to know, a little more about these, you can sort of search up their derivations. But I don't think they're that important if they're not in my slides. So just memorize these. That would be all. And okay, our next topic will be 28.5. It still goes on in drop. God. Crossed fields. I am going to lose it, my God. Crossed fields. This time, the all of it. Why do you keep doing that? Whatever. You know what? I think that that's unfortunately time we have studied up until, well, nearly all of it in my, oh no, I apologize, that is not all of it. I guess half of it. Yeah, we've studied sort of half of it until 28.5. Afterwards, we'll do, I don't know when, I think in this weekend we'll do the rest of it, 28 and 29, possibly even the sample questions related to them. But for now, this is all. Thank you.